welcome to our deep dive today.
Oh, yeah.
Where we're going to be tackling a pretty fascinating topic.
Right.
Quantum Restricted Boltzmann Machines.
Mm-hmm.
Or QRBMs for short.
Yeah.
We're diving into an essay by Jörg O. Schneppat.
Okay.
That really explores this
kind
of mind-bending blend
right.
of quantum mechanics and AI and how those two things together could really kind of revolutionize the way we solve complex problems.
It's wild how Schneppat connects these two, like, seemingly disparate fields.
Yeah.
You have quantum mechanics, which is, like, operating on principles that just defy
our
everyday intuition. Yeah. And then you have AI, which is already, like, reshaping our world in these profound ways. But when you bring them together, you just open up this whole new realm of possibilities.
It's almost like you're giving AI a superpower.
Totally.
Right? It's like we're not just talking about, like, incremental improvements here.
No.
Schneppat suggests that QRBMs could lead to breakthroughs in fields like medicine, finance, even climate modeling.
Yeah, it's amazing.
But before we get carried away with all the potential, let's make sure we're both on the same page.
Yeah.
About like what a QRBM actually is.
Absolutely. So you're probably familiar with the idea of a Boltzmann machine. Yeah. Like working with those energy landscapes to kind of find the best solution.
Right.
A restricted Boltzmann machine, or RBM, streamlines that process.
Got it.
And now a QRBM takes that concept to a whole new level by replacing classical bits with these qubits.
Okay, qubits.
Yes.
Those quantum bits that operate under a completely different set of rules.
Right.
I remember reading about superposition, where a qubit can be in multiple states at once.
Yeah.
And that always trips me up. It's such a weird concept. It's like a coin spinning so fast, it's just a blur, and it's like existing in both heads and tails simultaneously.
That's a great way to visualize it.
Yeah.
That's the power of superposition.
Okay.
And it's not just some theoretical quirk.
Right.
It has real computational implications.
Okay.
So while a classical computer has to explore each solution path one by one, a QRBM with its qubits in superposition can explore multiple paths concurrently.
So it's like having a massive parallel processing system just built into the fabric of a computation. That's where the real speed advantage comes in. Right?
Exactly.
Especially for those problems.
Right.
That would take classical computers like an eternity to solve.
Absolutely.
Yeah.
And then you add entanglement to the mix.
Okay.
Where these qubits become interconnected in a way that even Einstein called spooky action at a distance.
Yeah.
And that further amplifies the computational power of QRBMs, allowing them to tackle problems in a way that just wouldn't be possible with classical systems.
So Schneppat goes on to highlight some of these potential real-world applications of QRBMs. And this is where things get really exciting.
Totally.
He talks about logistics and traffic planning, where QRBMs could optimize everything from delivery routes to resource allocation.
It's amazing.
In real time.
Imagine a city where traffic flows smoothly.
Right.
Deliveries arrive on time.
Yeah.
Resources are used efficiently.
Yeah.
All thanks to the power of QRBMs.
Yeah.
Crunching these massive amounts of data and making optimal decisions on the fly.
It's amazing.
That's just one example of how this technology could transform our daily lives.
He also mentions drug discovery.
Yes.
QRBMs could potentially accelerate the process by simulating how different molecules interact with target proteins, leading to faster identification of potential drug candidates.
It's like having this quantum chemist working tirelessly to sift through millions of molecules and pinpoint the ones that could lead to new cures.
And let's not forget about finance.
Oh, yeah.
QRBMs could be used to analyze global market trends in real time, making predictions with a level of accuracy that could protect investors from financial crashes and help them make smarter investment decisions.
Absolutely.
It does feel like we're on the cusp of something truly revolutionary.
Right.
But I know SNEPPAT also addresses the challenges that still lie ahead.
Of course.
It's not all smooth sailing in the quantum realm.
Of course not.
Yeah.
There are significant hurdles to overcome.
Yeah.
One of the biggest is this issue of decoherence.
Right.
Where qubits lose their quantum properties over time due to interactions with their environment.
So it's like the quantum magic fades away.
Exactly.
Leading to errors in computations. And that seems to be like a fundamental challenge.
It is.
Not just a technical limitation that we can easily engineer our way out of.
It's a complex issue, and researchers are working on various strategies to mitigate decoherence.
Yeah.
But it's definitely a factor that needs to be addressed if we want to unlock the full potential of QRBMs.
Another challenge I recall from the essay is the limitations of current quantum hardware.
Yes.
We're still in the early days of quantum computing.
Yeah.
And the number of qubits that we can reliably work with. Is relatively small.
That's right. Building large-scale, fault-tolerant quantum computers.
Right.
It's a formidable engineering challenge.
Yeah.
But progress is being made, and we're seeing steady increases in the number and stability of qubits.
So it sounds like there's this race going on.
Yeah.
Between
it's like a race?
The theoretical capabilities of QRBMs and the practical limitations of the quantum hardware.
Exactly.
It's exciting to think about what might happen when those two finally converge.
Absolutely. It's a fascinating time to be following this field.
Yeah.
And SNEPPAT's essay does a fantastic job of capturing both the immense potential and the very real challenges that lie ahead.
I agree.
It's a must-read.
We've covered a lot of ground already.
Yeah.
From the fundamental principles of QRBMs to their potential applications and the challenges that stand in their way.
Right.
But there's still so much more to explore.
Definitely. We've only just begun to scratch the surface of this really exciting field.
For sure.
Yeah.
Okay.
All right. SNEPPAT doesn't just stop at the, theoretical potential, though.
Right.
He actually dives into the specifics of how we might actually, build and implement these QRBMs.
So he talks about
He does.
The hardware.
Yeah. He mentioned some of the leading contenders in the quantum hardware arena. You got your superconducting qubits, trapped ions, photonic systems. It's like this whole new world of possibilities.
It is.
It really is. And each approach has its own strengths and challenges.
Right.
Superconducting qubits, for example, require these ultra-low temperatures, which is a feat of engineering in itself.
It's like creating a mini quantum universe here on Earth.
Totally.
And companies like IBM and Google, they're making impressive strides in this area.
They are.
With their quantum processors.
And then you have trapped ions, which involve manipulating, individual atoms with lasers.
It sounds like something.
It does.
Straight out of science fiction.
It really does.
But it's a very real and promising avenue of research.
It is very promising.
Yeah, it makes you wonder, what other seemingly impossible technologies might be just around the corner.
Exactly. And let's not forget about photonic systems, which leverage the power of light photons as qubits. These systems have the advantage of being easily integrated with existing optical networks, which could be a game changer for communication and data transfer.
So we have this diverse array of quantum hardware options.
Right.
But how do we actually bridge the gap?
That's a great question.
Between the hardware and the problems we want to solve.
That's where the magic of quantum algorithms comes in.
Okay.
These algorithms are specifically designed to harness the unique capabilities of quantum computers, like superposition and entanglement.
So it's not just about having...
It's not just about the raw power.
Right.
It's about having the right instructions, the right set of tools to kind of orchestrate that power. Precisely. And one of the key algorithms for QRBMs is quantum sampling. It allows us to efficiently explore this vast landscape of possible solutions and identify the best one without having to evaluate every single option.
So it's like having a quantum compass.
Yeah, it's a great analogy.
That guides us through
is
this maze of possibilities.
Yeah. Can you give us a concrete example of how this might play out in a real world scenario? Certainly. So imagine we're tasked with designing a new material with specific properties, maybe something lighter, stronger and more durable than anything we have today. With quantum sampling, we can use a QRBM to quickly evaluate a vast number of potential molecular configurations and pinpoint the ones that meet our criteria.
So instead of blindly experimenting in the lab, we can use the QRBM to guide our search and focus on the most promising candidates.
Absolutely.
That could dramatically accelerate the pace of materials discovery.
Exactly. And it's not just limited to material science. This same principle can be applied to a wide range of problems. From optimizing financial portfolios to developing personalized medicine.
It sounds like quantum sampling is a real game changer.
The game changer.
But, as with any emerging technology, there are bound to be,
of course,
some roadblocks along the way.
Roadblocks for sure.
What are some of the challenges that we still need to address?
As we discussed earlier, decoherence remains a significant hurdle. It's this tendency for qubits to lose their quantum coherence over time.
It's like the qubits are constantly being bombarded by noise. And that noise disrupts their delicate quantum dance.
That's a great analogy. And this decoherence can introduce errors into our calculations, which can compromise the accuracy and reliability of our results.
So it's not just about building...
It's not just about building bigger, more powerful quantum computers. It's also about making them more robust and resilient to this decoherence effect. Precisely. And then there's the challenge of scalability. While we've made impressive progress in building quantum computers with dozens or even hundreds of qubits, we're still a long way from having systems with the thousands or millions of qubits that would be needed to tackle some of the most complex problems.
So the hardware's still catching up to the ambitions of our algorithms.
It is, but researchers are working tirelessly to overcome these challenges. They're developing new techniques for error correction, exploring novel qubit architectures, and pushing the boundaries of quantum control.
It's encouraging to see the progress is being made.
It is.
On multiple fronts. But in the meantime, are there any ways to work around these limitations and start exploring the potential of QRBMs today?
One promising approach is to use hybrid quantum classical systems. These systems combine the strengths of both classical and quantum computing, allowing us to leverage the best of both worlds.
So it's like a tag team effort.
It is.
Where each type of computer handles the tasks it's best suited for.
For example, we can use classical computers to perform the initial data processing and then hand off the more computationally intensive tasks to the quantum computer.
That makes a lot of sense.
It does.
It's a pragmatic way to start reaping the benefits of quantum computing even before we have fully fault-tolerant and scalable quantum systems.
Precisely. And these hybrid systems are already being used to explore a variety of applications, from drug discovery to material science.
It's exciting to see that we're not just
waiting around for the perfect quantum computer to arrive. We're finding creative ways to harness the power of quantum computing today.
Absolutely. It's a testament to the ingenuity and determination of these researchers in this field.
It really is.
This deep dive into QRBMs has been truly eye-opening. It's clear that we're still in the early stages of this quantum revolution. But the potential
is immense.
It's huge.
I agree. We're just beginning to glimpse the possibilities that lie ahead. And it's going to be an incredible journey to witness how this technology unfolds.
Totally. It feels like we're standing on the edge of a new frontier.
It does.
With these QRBMs, like we have this powerful new tool and we're just starting to understand what we can build with it.
That's what makes this whole field so exhilarating. Shinapat's essay really captures that sense of wonder and possibility.
For sure.
He doesn't just lay out the technical details. He invites us to imagine what might be achievable with this technology.
He paints a picture of QRBMs tackling some of humanity's biggest challenges. One that stood out to me was climate change.
Yeah.
It's such a complex system.
It is.
With so many variables. Could QRBMs really help us?
That's the hope.
Make sense of it all.
Imagine QRBMs analyzing these vast data sets of climate information, modeling weather patterns, predicting future scenarios, even identifying potential solutions.
Wow.
The sheer computational power could give us a much deeper understanding of how our climate is changing and what we can do to mitigate the damage.
That would be a game changer.
It would?
And what about other areas? I remember Schneepat mentioning material science.
Exactly. Think about designing new materials with unprecedented properties. Lighter, stronger, more sustainable materials that could revolutionize industries. From aerospace to construction. QRBMs could help us discover those materials much faster. Sifting through
potential molecular configurations with incredible speed and precision.
It's like having a quantum-powered design lab working tirelessly to create the materials of the future.
Exactly.
And of course, we can't forget.
Of course not.
About the impact on artificial intelligence itself.
Right. QRBMs could lead to the development of far more sophisticated AI systems. Capable of learning and adapting. In ways we can only dream of right now.
Wow.
Systems that could solve problems. That just seem intractable to us today.
It's mind-blowing.
It is.
To think about the possibilities. But as with any powerful technology, it's important to consider,
of course,
the ethical implications as well.
Yes.
Schneepat doesn't really touch on that.
He doesn't.
In his essay.
Wow.
But it's something we need to keep in mind.
We do.
As this technology evolves.
Absolutely. We need to have
these open and honest conversations about the potential societal impact of QRBMs and ensure that they are developed and used responsibly. But for now, I think it's okay to let our imaginations run wild.
For sure.
With the possibilities.
So what's next?
That's a great question.
In this quantum adventure.
Yeah.
What needs to happen for QRBMs to reach their full potential?
A lot of the groundwork has already been laid by researchers like Schneepat, but we still need to see significant advances in quantum hardware.
So like more qubits.
More qubits, longer coherence times, better error correction. These are all crucial areas for future development.
And on the software side,
we need to continue refining those quantum algorithms, tailoring them to specific problems, and making sure they can fully exploit the power of the hardware.
Got it.
It's an ongoing process of co-evolution between the hardware and the software.
It's fascinating to think about.
It is.
How these two sides, the theoretical and the practical, are coming together to drive this field forward.
They are.
And it's clear that we're just at the beginning of this journey.
Exactly. We've only just scratched the surface of what's possible with QRBMs and quantum machine learning in general. There are sure to be surprises and breakthroughs along the way. It's an exciting time to be alive.
I agree.
And witnessing this technological revolution unfold.
A huge thank you to Jorgo Schneepat for giving us such a thought-provoking glimpse into this world of QRBMs.
It's a must-read.
His essay is a must-read for anyone who wants to understand where computing might be headed.
I couldn't agree more. It's a call to action to embrace the power of these machines and explore the uncharted territories of quantum machine learning.
And to our listeners, we'd love to hear your thoughts. If QRBMs could achieve their full potential, what problem would you want them to solve?
What kind of quantum-powered future do you envision?
Let us know.
Let us know.
In the comments.
It's time to start imagining the unimaginable.
Thanks for joining us on this deep dive. Into the world of quantum restricted Boltzmann machines.
Absolutely.
We'll see you next time.
See you next time.
For another fascinating exploration of the cutting edge of science and technology.